In computability theory, a system of data manipulation rules is said to be Turing complete or computationally universal if it can be used to simulate in any single-taped Turing machine. The concept is named after English mathematician Alan Turing. A classic example is lambda calculus. A closely related concept is that of Turing equivalents. Two computers P and Q are called equivalent if P can simulate Q and Q can simulate P. According to the Church-Turing thesis, which conjectures that the Turing machines are the most powerful computing machines, for every real-world computer there exists a Turing machine that can simulate its computational aspects. Universal Turing machines can simulate any Turing machine and by extension the computational aspects of any possible real-world computer. To show that something is Turing complete, it is enough to show that it can be used to simulate some Turing complete system. For example, an imperative language is Turing complete if it has conditional branching and the ability to change an arbitrary amount of memory locations. Since this is almost always the case, most imperative languages are Turing complete if the limitations of finite memory are ignored. Non-mathematical usage. In colloquial usage, the terms Turing complete or Turing equivalent are used to mean that any real-world general-purpose computer or computer language can approximately simulate the computational aspects of any other real-world general-purpose computer or computer language. Real computers constructed so far are essentially similar to a single-taped Turing machine, thus the associated mathematics can apply by abstracting their operation far enough. However, real computers have limited physical resources, so they are only linear-bounded automaton complete. In contrast, a universal computer is defined as a device with a Turing-complete instruction set, infinite memory, and infinite available time. Formal definitions. In computability theory, several closely related terms are used to describe the computational power of a computational system. Turing completeness. A computational system that can compute every Turing computable function is called Turing complete. Alternatively, such a system is one that can simulate a universal Turing machine. Turing equivalents. A Turing-complete system is called Turing equivalent if every function it can compute is also Turing computable, i.e., it computes precisely the same class of functions as do Turing machines. Alternatively, a Turing-equivalent system is one that can simulate, and be simulated by, a universal Turing machine. Universality. A system is called universal with respect to a class of systems if it can compute every function computable by systems in that class. Typically, the term universality is tacitly used with respect to a Turing-complete class of systems. The term weakly universal is sometimes used to distinguish a system whose universality is achieved only by modifying the standard definition of Turing machine so as to include input streams with infinitely many 1s. History. Turing completeness is significant in that every real-world design for a computing device can be simulated by a universal Turing machine. The Church-Turing thesis states that this is a law of mathematics, that a universal Turing machine can, in principle, perform any calculation that any other programmable computer can. This says nothing about the effort needed to write the program, or the time it may take for the machine to perform the calculation, or any abilities the machine may possess that have nothing to do with computation. Charles Babbage's analytical engine would have been the first Turing-complete machine if it had been built at the time it was designed. Babbage appreciated that the machine was capable of great feats of calculation, including primitive logical reasoning, but he did not appreciate that no other machine could do better. From the 1830s until the 1940s, mechanical calculating machines such as adders and multipliers were built and improved, but they could not perform a conditional branch and therefore were not Turing complete. In the late 19th century, Leopold Kronecker formulated notions of computability, defining primitive recursive functions. These functions can be calculated by rote computation, but they are not enough to make a universal computer, because the instructions which compute them do not allow for an infinite loop. In the early 20th century, David Hilbert led a program to axiomatize all of mathematics with precise axioms and precise logical rules of deduction which could be performed by a machine. Soon, it became clear that a small set of deduction rules are enough to produce the consequences of a set of axioms. These rules were proved by Kurt Gödel in 1930 to be enough to produce every theorem. However, they will always prove some theorems as both true and false, for an axiomatization not simpler than Peano arithmetic. The actual notion of computation was isolated soon after, starting with Gödel's incompleteness theorem. This theorem showed that axiom systems were limited when reasoning about the computation which deduces their theorems. Church and Turing independently demonstrated that Hilbert-Scheidung's problem was unsolvable, thus identifying the computational core of the incompleteness theorem. This work, along with Gödel's work on general recursive functions, established that there are sets of simple instructions, which, when put together, are able to produce any computation. The work of Gödel showed that the notion of computation is essentially unique. Computability theory. The first result of computability theory is that it is impossible in general to predict what a Turing-complete program will do over an arbitrarily long time. For example, it is impossible to determine for every program input pair whether the program operating on the input will eventually stop or will continue forever. It is impossible to determine whether the program will return true or whether it will return false. For any characteristic of the program's eventual output, it is impossible to determine whether this characteristic will hold. This can cause problems in practice when analyzing real-world computer programs. One way to avoid this is to cause programs to stop executing after a fixed period of time, or to limit the power of flow control instructions. Such systems are not Turing-complete by design. Another theorem shows that there are problems solvable by Turing-complete languages that cannot be solved by any language with only finite looping abilities. Given a guaranteed halting language, the computable function which is produced by Cantor's diagonal argument on all computable functions in that language is not computable in that language. Turing oracles. A computer with access to an infinite tape of data may be more powerful than a Turing machine. For instance, the tape might contain the solution to the halting problem, or some other Turing undecidable problem. Such an infinite tape of data is called a Turing oracle. Even a Turing oracle with random data is not computable, since there are only countably many computations but uncountably many oracles. So a computer with a random Turing oracle can compute things that a Turing machine cannot. Digital physics. All known laws of physics have consequences that are computable by a series of approximations on a digital computer. A hypothesis called digital physics states that this is no accident, that it is because the universe itself is computable on a universal Turing machine. This would imply that no computer more powerful than a universal Turing machine can be built physically. Examples. The computational systems that are discussed as Turing-complete systems are those intended for studying theoretical computer science. They are intended to be as simple as possible, so that it would be easier to understand the limits of computation. Here are a few. Automata theory. Formal grammar. Formal language. Lambda calculus. Post-Turing machines. Most programming languages, conventional and unconventional, are Turing-complete. This includes all general-purpose languages in wide use, procedural programming languages such as C, Pascal, object-oriented languages such as CIL, Java, Smalltalk, Multi-paradigm languages such as Ada, C++, Common Lisp, Object Pascal. Most languages using less common paradigms. Functional languages such as Lisp and Haskell. Logic programming languages such as Prolog. Declarative languages such as XSLT. Esoteric programming languages, a form of mathematical recreation in which programmers work out how to achieve basic programming constructs in an extremely difficult bit. Mathematically Turing equivalent language. Rewrite system. Universal Turing machine. Turing completeness is an abstract statement of ability, rather than a prescription of specific language features used to implement that ability. The features used to achieve Turing completeness can be quite different. Fortran systems would use loop constructs or possibly even goto statements to achieve repetition. Haskell and Prolog, lacking looping almost entirely, would use recursion. Turing completeness in declarative SQL is implemented through recursive common table expressions. Unsurprisingly, procedural extensions to SQL are also Turing complete. This illustrates one reason why relatively powerful non-Turing complete languages are rare. The more powerful the language is initially, the more complex are the tasks to which it is applied, and the sooner its lack of completeness becomes perceived as a drawback, encouraging its extension until it is Turing complete. The untyped lambda calculus is Turing complete, but many typed lambda calculi, including System F, are not. The value of typed systems is based in their ability to represent most typical computer programs while detecting more errors. Rule 110 and Conway's game of life, both cellular automata, are Turing complete. On a lower level, any language that can simulate the underlying components is Turing complete. Hardware description languages like VHDL and Verilog are Turing complete, as they are both used to design chips that modern computers are made of. Minecraft, being able to emulate logic gates using its redstone and piston mechanism, is also Turing complete. Non-Turing complete languages. Many computational languages exist which are not Turing complete. One such example is the set of regular languages, most commonly regular or expressions, which are generated by finite automata. A more powerful but still not Turing complete extension of finite automata is the category of push-down automata and context-free grammars, which are commonly used to generate parse trees in an initial stage of program compiling. Further examples include some of the early versions of the pixel shader languages embedded in Direct3D and OpenGL extensions. In total functional programming languages, such as Charity and Epigram, all functions are total and must terminate. Charity uses a type system and control constructs based on category theory, whereas Epigram uses dependent types. The loop language is designed so that it computes only the functions that are primitive recursive. Also, since all functions in these languages are total, algorithms for recursively enumerable sets cannot be written in these languages. In contrast with Turing machines, although lambda calculus is Turing complete, simply typed lambda calculus is not. Data languages. The notion of Turing completeness does not apply to languages such as XML, HTML, JSON, YAML and S expressions, because they are typically used to represent structured data, not describe computation. These are sometimes referred to as markup languages, or more properly as container languages, or data description languages. However, Rule 110, a Turing-complete cellular automaton, has been successfully implemented in CSS, thus proving its Turing completeness.